Okay, in this video we're having a look at cubics in the form y equals a outside of x take h cubed plus k. Okay, so there's a couple of things that we need to remember here. Okay, so a quadratic can be written in the form y equals f of x equals a outside of x take h squared plus k. So that's any quadratic. Okay, so that works for all of them. This is not true for cubics. Okay, we don't have a completing the cubic process that we can do to put in this form. Okay, and it will make a little bit more sense of it later on. Okay, when we look at different forms of our cubics, why we can't change from one to the other, because they have different shapes to the graphs depending on what the form is. Okay, so what are we talking about with this then? Okay, with our f of x equals a outside of x take h cubed plus k. Now, funnily enough, this looks the same as what we're seeing time and time again with our different functions. The only thing we've changed now is this value up here is 3. It's the same as if it was 2, it's the same as if it's a half, okay? Same if it's -1 or -2, okay? We're seeing this form a lot, okay? So should hopefully just be a recap. Okay, so we talk about a being a dilation factor from the y-axis. So that's the thing that makes it narrow or wider, okay? Also, if a is less than 0, so that means it's negative, okay, it's a reflection in the x-axis. Okay, now a reflection in the x-axis and the y-axis is the same for a cubic. You'll see that in a moment when we sketch it. But strictly speaking, if it's written here, okay, it's a reflection in the x-axis. If this x value was made to be negative, it would be a reflection in the y-axis. But because a negative value cubed gives a negative value, we end up saying exactly the same thing. Okay, if we keep moving along, this h value in here, that's our translation in the x direction. Okay, so if our number in the brackets is negative, then we're moving it to the right. Remember, this is the one that is the different way to what we think. Okay, if it's positive, we move it to the left. Okay, k is that vertical translation. Okay, if k is positive, we move it up. Okay, if k is negative, we move it down. Okay, so let's have a look at some of these things. Okay, so tell me about sketching f of x equals x cubed and f of x equals x to the power of a third. Now this might seem unrelated, but you'll see how they're connected in just a moment. So this is what our basic graph looks like. Okay, and I can do a decent one. Oh, I need to make that a little bit nicer for you. Okay, it looks something like this. Okay, it picks up my axis here in the middle. Okay, but the important thing to note, okay, about this. Okay, we go through the point 1, 1. Okay, and we go through the point -1, -1. Okay, and my scale isn't very good on this graph, but we go through those 2 points. Okay, we also obviously go through the origin there, but what's important, okay, is this point here. Okay, is called a point of inflection. Point of inflection. Okay. Now, more strictly for this, it's a stationary point of inflection, and that's just because our gradient or slope of our graph is 0 here. Okay, so our gradient or our slope, we actually have a spot on our graph which is flat. Okay. And that's our stationary point of inflection. A point of inflection, okay, it's just a point where the graph goes from concave down to concave up. So we can see our curve is going this way, now it's going this way. So the concave side is pointing down, we'll switch to the concave side being pointing up. That's our idea of a point of inflection. Okay, so that's what it looks like. So when we look at our form, y equals a x take h cubed plus k, all we're doing is moving this thing around. Okay, so the h is going to move it left to right, and the interesting point that we care about is this point of inflection. So take that as your reference point. So the h is going to move it left and right. The k is going to move it up and down. The a doesn't move this point, but it stretches or compresses it out. Okay, why were we talking about f of x equals x to the power of a third? Okay, well that's because it's actually the inverse of f of x. Okay, and we've seen some inverses in our other work. So we have this line y equal x. Okay, then it's simply, actually I should change colours again, it's simply going to be our reflection in that line. Okay, so we do something like this. Okay, and that's our y equals x to the third, or f of x equals x to the third. Okay, we're going to intersect here at x equals 1, and intersect here at x equals -1 as well. Okay, remember they intersect on the line y equals x. Okay, so let's have a look at a couple of examples here. So we've got e.g. Okay, sketch y equals 2 outside of x take 1 cubed plus 2. Okay, first of all we're going to need some axes. Okay. Then we need to have a look at what's going on with our function. So 2 is going to dilate it. Okay, doesn't help us very much here. Okay, we tend to use that at the end. Okay, because we can look at that interesting point, that point of inflection, and see where it's moved. Okay, so point of inflection that was at the origin has been moved to the right by 1 unit. Okay, so we come across here. Okay, and we've been moved up by 2 units. Okay, so our point of inflection is going to be here now. Okay, point of inflection is going to be there. Okay, so we also need to think about that dilation factor, what that's going to do. What's easiest now is to actually have a think about our x and y intercept. So if we look at our y-intercept, okay, that's when x equals 0. So we have -1 cubed, okay, is -1. Okay, times 2 is -2, plus 2 is 0. Okay, so we're actually going through our origin. Okay, pretty easy. We don't need to worry about our x-intercept now because we know it is going to be there as well. So what we can do now is we can sketch it. Okay, making sure we do flatten it out there. Okay, and we come up. Now we haven't had to label another point. Okay, because as soon as we find an x or y intercept, that's another point. That indicates our dilation factor. We're taking care of it. So in these ones, you don't have to worry about finding another point other than your intercepts. Okay, that's going to show you any dilation factor you've got. Okay, if we didn't have that dilation factor 2, we would have come through here. Okay, so spread it out a bit. Okay, so our next example is sketching f of x equals -x plus 1 to the third, take 1. Okay, so this time we're looking at that inverse. So we can draw some axes up here. So remember our general shape is like that this time. Okay, so we still need to look at what's happened to our point of inflection. This time it's been moved to the left by 1. It's going to be here at -1, and it's also been moved down by 1. Okay, so our point of inflection is going to be there. Okay, now usually we would go this sort of shape, like that. Okay, but we've got this negative here, so that means it's being reflected. So this time we're going to come down. Okay, so we need to work out some intercepts here, and that'll help us out. So when x is 0, okay, we have 1 to the power of a third is just 1, okay, times -1. Okay, so we've got, sorry, we'll put this in. So we've got 0 take plus 1. Okay, take 1. Okay, so we've got 1 to the power of a third. Okay, well that's just going to be 1 times -1. Okay, is going to be -1. Take 1 equals 2. Okay, so that's going to be, sorry, -2. Okay, so that was our y-intercept. So we're crossing here at -2. Okay, and that makes sense because we're coming through and down. Okay, so if we want to find our x-intercept, okay, we've got to say that now y is 0. So we've got 0 equals -x plus 1 to the 1/3. Take 1, add 1 on. Okay, makes it 1. Okay, and then we're going to times by -1 as well to get rid of that negative. I'm going to say we've got x plus 1 to the power of a third. Okay, to undo the power of a third, we need to cube it. So everything, so -1 cubed is going to be -1 equals x plus 1. Okay, and then we take our 1 away, and we also we go through -2 for x. Okay, so what we can see is we're going to do this. Okay, something like that for our graph. Okay, so you can see that these things are very similar to what we've seen before in terms of the way the functions work, what each thing does. Okay, all we're doing now is looking at what the shape of our graph is. So hopefully that'll be enough to help you out with some of these questions.